Hi, everybody. Welcome to OWLS. Thanks a lot for joining us. Today, we're delighted to have Bartek Klin from the University of Warsaw talking to us about monadic second-order logic. Before we get underway, let me just remind you a few of the ground rules of OWLS seminars. Please keep your video on as much as you can. This lets it easy for people to see who's around. Zoom uses bandwidth very intelligently, so it doesn't really disrupt the experience for other people. You can switch between speaker view and gallery view if you don't want to have to see everybody simultaneously. You'll be forcibly muted during the seminar, so you can't accidentally interrupt. If you have a question for the speaker, please raise your hand. You can do that by selecting raise hand in the options at the bottom of the screen. The seminar is being recorded, but you will only be included in the recording if you ask a question. So if you don't want to be recorded, then please don't ask a question. And of course, the coffee breaks, the informal discussions that we have before and after the seminar are not recorded. The chat room is disabled during the seminar, but you can send a private message to me. So if anything seems technically wrong with the setup, please send me a private message. In particular, if you think there's any participant here who's not here for the right reasons, please send me a message and we can see what we can do about that. So without further ado, let me hand over to Bartek.
Thank you, Jamie, and thank you so much for the invitation, and thank you all for coming. First, I should a brief remark about the title of this presentation. The word monadic does appear twice in the title in two different meanings. This monadic here means of arity one, and this logic will be of arity one, and the monadic second order logic is a completely standard concept that I will recall briefly. This monadic here means related to a monad, and monads are another completely standard concept that I will also recall briefly, and the idea in this talk will be to combine the two, the two concepts. Now, why? The story is best started with, with regular languages. Regular languages of finite words. So there are several equivalent definitions of what it means to of the class of regular languages. One definition is those languages that are accepted by finite automata, which we all know and like, I suppose. Another definition is languages defined by regular expressions. Yet another definition is languages of words, languages that are MSO definable, definable in monadic second order logic. This is a second order logic with first order and second order variables, the inclusion predicate. Then on first order, the idea is, okay, let me show a full slide of it, what the monadic second order logic is. In monadic second order logic, we treat words as relational structures where elements of the structure, element of the universe, are just positions in the word. And then the language that we use is, we have a less than predicate, that's a binary relation, that is just says whether a position occurs before another position. And then in a word, additionally, certain positions satisfy predicates related to elements of the alphabet, of the letters. So those positions where a letter A occurs satisfies a unary predicate QA, and similarly for every other letter in the alphabet. This is a relational structure that we can work on, and we can formulate properties on it using monadic second order language. So, for example, there is this formula here that says that every A is followed by a C, if I wrote it correctly. This is actually a first order formula, and a famous example of a property. And the language described by this formula is regular. And the famous example of a property that cannot be defined in first order, but it can be in monadic second order, is the property of the length of the word being even. This is the formula, and it starts with an existential quantification, second order quantification, saying there exists a set of positions which intuitively mean the set of odd numbered positions. So this is this is how monadic second order logic is. I won't say very much about it, because contrary to what the title says, I will actually use this logic very little in this form, in this syntactic form. Anyway, there is a theorem, and it's not difficult to prove, that MSO definable languages of finite words are also exactly regular languages. And then yet another definition is languages recognized by finite monoids. So how does this work? So the set for any alphabet sigma, the set sigma star, is a monoid. And then we can consider a monoid homomorphism from this monoid to another one, let's say a finite monoid M. And then if we consider additionally a subset of this finite monoid, then the inverse image of this subset along H is a language, is a subset of sigma star. And this language, then we say that is recognized by the monoid, the homomorphism, and the subset, the three things taken together. And it turns out that languages recognized by finite monoids are also exactly regular languages. So all these definitions are equivalent. And the idea is, the idea of not just this talk, but there's a whole line of research to generalize this picture from finite words to other things. Okay, and this is what's been going on. And in this talk, I will focus on the equivalence at the bottom of MSO definability and recognizability by finite monoids or algebras. What things shall we consider? In this talk, there are many things that people have considered in this area. But for this talk, there's a framework that I will describe in this talk. Will cover things like finite words, infinite words, countable words or countable total orders, scattered total orders of sizes, modes, continuum, and so on, finite trees. So this will be covered. These will not be covered, although it has been, they have been studied in this context, in sort of concrete settings. And I won't cover them, mostly to keep presentation simple. For those of you who know categories, I will try to stay in the category of sets rather than moving to slightly more complex categories such as ranked sets or multi-sorted sets. That's the sort of step that would be required to cover more fancy example. But perhaps interestingly, I will also cover several other things that will not have been too obvious to people study language theory in the beginning. It will turn out that our framework will cover that quite naturally. Okay, so here's the equivalence that I want to study. And actually, I want to restrict my focus even more. I want to restrict to one implication of this equivalence. So traditionally, when people study this equivalence for MSO definability and recognizability for settings such as infinite words or finite trees, the right to left implication is quite easy for simple cases, such as finite words, but it is difficult or even open for more complex examples. And when it holds, it often holds for deep reasons. And it seems that for each case, the argument is sort of structure specific. So it will be hard, we think, it will be hard to get a generic understanding of when this implication holds. On the other hand, the left to right implication, in the simplest cases, it is considered slightly less easy than the right to left, but it generalizes quite naturally to other cases. It also holds for other cases, and the argument looks the same if you look at it. So there is some hope of actually proving it once and for all. And this is what we'll try to do. But before I do that, to transport all these even notions, not just the results, but notions from finite words to other structures, I will need to, well, do some work. And before I do that, let me propose, let me give you another equivalence. For finite words, at least, MSO definable languages or regular languages are also the least class of languages over finite alphabets closed under the following operations. First of all, the language 0 star 1 star over a 2-letter alphabet is in this class, and then it is closed under Boolean combinations, inverse images along homomorphisms, along language homomorphisms, that we can replace a letter by a word, and direct images along surjective letter-to-letter homomorphisms. It turns out this is not hard to prove, and it looks pure bureaucracy. There's very little going on in this proof if you look at it. So it makes sense to see this as a sort of syntax-free definition of MSO, of monadic second-order logic, which looks a bit more generic than this original definition, which relies on some structure-specific predicates, and it's not clear how to derive the predicates for other structures. This looks a bit more generic, and also it still looks like a logic in the sense that this class defined by this is defined as the least class closed under certain operations, which supports inductive reasoning, which is one of the purposes of the logic if you disregard proof systems. So this is what we will take, in fact, and as our abstract definition of MSO. All right. And then we will focus on the left to right implication. So before I even formulate this for arbitrary structures, let me show you very briefly how this implication is proved for finite words, to see that it is very easy and mostly actually trivial. So first of all, so I want to show that the least class of languages, if a language belongs to this least class, then it is recognized by a finite monoid. So first of all, this language is recognized. We just find the monoid, it has 5 elements or something. Then, if you have 2 languages, L1 and L2, and they're both recognized by some finite monoids, and you want to recognize their sum or union, well, you just construct the monoid on the product monoid of those 2. You choose the recognizing subset suitably, depending on whether you want to recognize the sum or the union, the union on the intersection. I'm sorry, and then you recognize. That's easy. For the complement, it's even easier. Actually, the same monoid does the job. You just switch the accepting set. And then for the inverse image along homomorphisms, that's even easier, because if you have a language recognized by some homomorphism, and then you get a homomorphism from another language, then the composition of the 2 homomorphisms recognizes the inverse image. Okay, so that's completely trivial, in fact. It is slightly less trivial, but still not too bad for direct images of letter-to-letter homomorphism. The way it works is like this. So suppose I have a language over some alphabet sigma, and I have a translation or a homomorphism from sigma to some alphabet gamma. All right. What I do is I first define the monoid on the power set, on the set of subsets of M. I'm sorry. Which is easy to do in the standard way. And then I define a certain homomorphism from gamma star to Pm, with the intuition being that K of a word gives you the set of all elements of M that can be obtained by H applied to some words that are mapped to our word by G star. That's the idea. This is how K is defined, and then you suitably choose the subset of this, and it actually happens to recognize the direct image of L along G or G star, whatever you define it. Okay. So this is how this is proved for finite words. It's easy, but slightly less trivial than than all the remaining cases. Okay. Now I want to move. So we have just shown that the class of languages recognized by finite monoids is closed under Boolean combinations, inverse images along homomorphisms, and direct images along surjective letter-to-letter homomorphisms. And now the question is, how to generalize this to other kinds of structure. First of all, how to formulate it for other kinds of structures, and then how to prove it. And other kinds of structure will be monads. So 2 weeks ago, Daniela talked extensively about monads. So it looks like everybody should know what monads are. I will very briefly recall what monads are. For the minority that might not know it. So the intuition for me, there are several different intuitions behind monads. The intuition for me that monads will be ways to collect stuff. So a monad T given a set X returns a set which we call Tx, and the idea is that this Tx will be the set of collections of a certain kind of elements of X. These are examples. This extends to functions, so that some simple axioms are satisfied. This is called the functor on the category of sets, if you want to be very specific, but sets will be all I do in this talk. Then, moreover, a monad must come equipped with two natural transformations, what is called the unit. The intuition is that for any set X, we must be able to build singleton collections. And then multiplication, we should be able to flatten collections of collections into collections of X. Both these must be natural, meaning that they act the same for every set X intuitively. And then two axioms hold, roughly, saying that if you flatten a singleton collection, you get the element of it, and so on and so forth. So this is the definition of a monad. That's completely standard. And the idea is that I want to generalize the story of connecting MSO definability and recognizability by monoids from the monad of finite words, which is an example of the very easy example of a monad, to other monads. Okay, so what do I need to do? What do I need to do for that? First of all, there are some examples: the list monad or the finite words monad, the power set monad, where the unit is, well, the singleton operation, and multiplication is union. Then the reader monad, which is, I think, the second monad that Haskell programmers learn in their Haskell education. So the reader monad Tx is the set of infinite words or omega words of elements of X. Tf applies F to such a word element-wise. Then the unit of X is the infinite word that repeats X infinitely many times. And then if I have an infinite word of infinite words, what the multiplication returns, or what the flattening returns, is the diagonal word of this infinite matrix. Okay, so that's the reader monad. It will be an example later. And then perhaps more generally, but it's also a very useful source of monads, and it's very convenient way to present them, is considering term monads. So if you have an equational presentation, meaning an algebraic language and some equations between the terms, then we can say that Tx is a set of sigma terms over X modulo the equations. Tf for a function f is variable substitution. Eta says that a variable is a term, and treats a variable as a term, and then mu, given a term build of terms, returns the flattened version of that term. So that's called the term monad, and many examples are very conveniently presented in this way. Now, this is the result that I've proved for finite monoids. We already know, if I replace finite words by any monad, I already know what a language is. So now my alphabet will be a set, ideally a finite set. T will be a monad now. Instead of the finite word monad, it will be an arbitrary monad on set. And then L over an alphabet sigma is just a subset of T sigma. That's what the language is. Boolean combinations, by the way, immediately come for free, because these are now subsets, so I can take their complements, unions, and intersections. Now, one question is, okay, what do I replace monoids with? Fortunately, if you know monads, there is an answer that stares us in the face: algebras for the monads. So Eilenberg-Moore algebras. So a T algebra is for a monad T is a set X, the universe or the carrier, and then a function from Tx to X such that two axioms are satisfied. For example, the monads for, I'm sorry, the algebras for the star monad for the finite word monad are monoids. Algebras for the power set monad are semilattices, and then if you take a term monad, then algebras for the monad are what you expect. If you take a term monad arising from an equational presentation, then a T algebra for that monad is actually an algebra for that algebraic signature that satisfies the equations that are present in the presentation. Okay, and then so that's a completely standard definition. There is also a notion of homomorphism. So if we have two algebras like that, one on a set X and another on a set Y, then a homomorphism from F to G is a function from one universe to the other that satisfies a certain axiom, and that's exactly the homomorphism condition that you see in various concrete examples. Now, what do I mean by recognizing a language with algebra? That's also a very old idea. I think it goes back to Eilenberg. First of all, there is a fact that the multiplication on a set X is always a T algebra that just follows directly from the axioms without any real proof. And then if I have a language over, I can say that if I have a language over an alphabet sigma, if I am able to find an algebra for the monad which is finite and choose a subset of this algebra so that the language L is the inverse image of H along inverse image of A along H, then we say that this language here is recognized by H, or by H, M, and A, by this triple. Yeah, but it is recognized. So the definition, the classical definition of recognized by finite monads is directly related to algebras. That's not so that's very simple. So I know what. So and I know what a language is. What do I mean by an algebra? What do I mean to be recognized by an algebra? Well, I know what homomorphism of algebra is now. Perhaps there is also one slight question. What do I mean by letter-to-letter homomorphisms? But this is also easy to formulate. So letter-to-letter homomorphisms between free algebras are of the form TF, where F is a letter-to-letter translation between alphabets. So I can also understand this, which means that the statement that was true for finite words can now make sense for arbitrary monads. Okay, I can formulate it as a property. Now, of course, the question is it true for every monad? If you recall, the proof of this statement for the monad of finite words was rather simple. So the question is, does it transport to other cases? And the answer is no. Boolean combinations are fine. Inverse images along homomorphisms are fine, with the proofs exactly as for the case of finite words. Nothing changes there. They were the trivial cases. But the not trivial but easy case turns out to fail for some examples of monads. So let me show you a counterexample. Okay, the counterexample will be a quotient monad of the finite word monad, which is very convenient because it is easy to we have good intuitions about finite words. So I'm sure you will understand the example. So the monad is the list monad, the finite words monad, quotiented by this equation: x cubed equals x squared. Okay, this I will call the Brzozowski equation, because as it turns out, this equation is a part of a very nice open problem in language theory posed 40 years ago by Brzozowski, who asked whether all congruence classes on finite words of this equation are regular languages. That's open. There are infinitely many classes. There are infinitely many congruence classes because every square free word is an element on its own. It's a singleton. It's not equivalent to anything because there is no way to apply this equation anywhere in a square-free word. So there are infinitely many equivalence classes. Obviously, singleton equivalence classes are regular, but the question is every equivalence class regular? That's been open. But I'm not going to solve this. I'm not going to solve this question. But I will use this equation. To construct a crazy counterexample. So first of all, a language for this monad, a subset of T sigma, because elements of T sigma are certain congruence classes of words. So such a language can be seen as a language of classical words, just finite words, which is closed under this equivalence, understood as a congruence. So I can apply this. If I can apply this equation to subwords, then I can see such a language as a language of words closed under B. Okay. A T algebra, using the same analogy, is just a monoid. So it's an algebra for this monad, which additionally satisfies this Brzozowski equation. Okay. So this is all can be understood in terms of monoids satisfying an additional equation and languages of finite words closed under a certain equation. And then the fact, which is very easy to prove, is that such a language is T recognizable if the corresponding, if when understood as a language of classical words, it is first of all regular, so it is recognized by finite monoids, and closed under Brzozowski. Okay, so there's no real content in this fact. It's easy to prove. How to build a counterexample now? Okay, so let's take a 3-letter alphabet, ABC. The 3 will be important, and then let's throw in 2 additional letters. So altogether, my sigma will have 5 elements, and my language over sigma, the language of words, will be delta star 0 delta 1. So this is the language of words. First of all, there are some ABCs, then 0, then some IBCs, then 1. Okay? This is obviously regular. It is also closed under the Brzozowski equation, because well, let's say that we have a word in here and we apply the Brzozowski equation to it. It means that this word contains a square somewhere, or a cube, which implies a square anyway. So now, because I have exactly 1, 0 and exactly 1, 1 at the end, it means that this square must be contained fully under either in this part or in this part. So if I replace the square by the corresponding cube, I'm still in the language. Okay, so it is closed. So it means that this language is actually recognized by a finite T algebra. It is recognizable. Now let's have a homomorphism here. So this will be a homomorphism, a letter-to-letter homomorphism that identifies 0 and 1. All right. Now the direct image of this language L under this homomorphism is it's not exactly this language, because this language is not B closed, but it is the big closure of it, the closure of this language under the Brzozowski equation. And it turns out that the Brzozowski closure of this language is not regular. So it is not recognizable. It has no chance of being recognized. Why isn't this not regular? Well, if it were regular, then it would have finitely many Myhill-Nerode classes. So because my language, because my alphabet delta here had 3 elements, over these over a 3-letter alphabet, there are infinitely many different square-free words. So which means that there are some words V and W square-free, which are Myhill-Nerode equivalent for this language here. So if they are, so let's say they are Myhill-Nerode equivalent, but then V0, V0, V0 is in the direct image of L. But it turns out that, which means by the Myhill-Nerode equivalence, that V0, W0, V0 is also in TH of L. But this word here is square free. If V is square free, W is square free, and they are different, then this language is square, this word, sorry, is square free. So it is not equivalent to anything, but it is not also, it is not it is not of this form. So it has no chance of being equivalent of anything of this form. Okay? This is how you prove that this language is not regular. Okay, so we have a counterexample. What's the picture? So that we know that the property that we're looking for, that finitely recognizable languages are not closed, are closed under direct images of letter-to-letter homomorphisms. It doesn't hold for every monad. So for what monads does it hold? It holds for several standard examples, but we have one example where it doesn't. So what's the situation here? And here, when it becomes when it becomes interesting, we don't have a good idea of that. So let me sketch you the landscape of monads that we know. First of all, so I will call these monads Q-dish, meaning closed under direct images of surjective homomorphisms. It's not a very good acronym because it misses the letter-to-letter part, but with letter-to-letter it would be completely unpronounceable. So let's call them Q-dish. And we have a monad that is not Q-dish. On the other hand, there are many examples, such as finite words, infinite words, scattered words, that are firmly there. And that has been studied by other people, and it's okay. So what happens now? I will show you a bunch of sufficient conditions that imply that a monad is Q-dish. Okay. First of all, very easy thing. If T is finiteness preserving, if T preserves finiteness, meaning for finite sigma, T sigma is finite, then every language on a finite alphabet is recognizable. It is simply recognized by this free algebra T sigma because it is now finite by this property that T preserves finiteness. So for a completely trivial reason, this monads that preserve finiteness are Q-dish. Now the reason is trivial, but of course, there are monads that preserve finiteness for non-trivial reasons. So the power set monads are in this class. But for example, the free idempotent monoid monad is also there. But a proof that a free idempotent monad on a finite set is finite, it's not entirely trivial. Distributive lattices, Boolean algebras are examples. So there is this sufficient condition which is inhabited by a bunch of monads. Note that the classical examples here are not there. Okay. Another sufficient condition. We say that a monad is Maltsevian if, okay, I will speak in terms of term monads here, which is not very far at all from the generic case. If it admits an equational presentation where there is some ternary term with three variables that satisfies these two equations. So Txxy equals Tyxx equals y. It turns out that these monads are Q-dish. And the proof is not very hard. It's half a page. I won't give you the proof. Examples, okay? So the archetypical example, the paradigmatic example of a Maltsevian monad is the monad of groups, the free group monad, because this now, xy inverse z, this term you should think about if you're looking for a term that satisfies the Maltsev equation. Okay, so the monad of groups and various quotients of the monad of groups, such as abelian groups and so on, these are all Maltsevian and therefore Q-dish. Other examples include the monad of Boolean algebras. So this is a Maltsev term for Boolean algebras. That's a bit less obvious, but it is actually true. Also Heiting algebras. So these are all Maltsevian. Therefore they are okay for our abstract definition of monadic second order logic. So Boolean algebras are now actually in both classes because they also preserve finiteness, and there are also other additional cases. Okay. Still, we do not cover the originally intended examples here, but fortunately there is a third condition. So a monad is weakly Cartesian. That's a standard notion in category theory. A monad is weakly Cartesian if it preserves weak pullbacks and if all naturality squares for for the unit and multiplication are weak pullbacks. There's a word of explanation here. I'm not going to spend very much on it, but so this is just for the recording case. But for example, what does it mean that the unit of a monad is weakly Cartesian? Intuitively, it means that a non-unit element or a non-unit term never becomes a unit after a substitution of variables. So for example, the power set monad does not satisfy this property, because if we have a two-element set x, y, then after this is not a unit, this is not a singleton set, but after identifying x and y, it becomes a unit. Okay. So, and for the conditions for multiplication and for preserving weak pullbacks also translate to similar conditions. And the fact is that weakly Cartesian monads are okay, they are Q-ish. And the proof, the idea is that roughly for these monads, the power set construct this is where the power set construction works. Okay, and this proof is a bit longer, but it's not. Examples of such monads, this is standard. Weakly Cartesian monads are those that are presented by linear irregular equations. These are equations where the same set of variables appears on both sides of the equation, each exactly once. So for example, these two are okay, these two are not. But there are also other monads that are weakly Cartesian. So for example, the monad presented by a single binary operation up to this equation is also weakly Cartesian. Okay, so this covers now our originally intended examples, and also some others. Right, and that's it. This is all sufficient conditions that we know, and to me it is very annoying, because these three sufficient conditions are really all over the place. They have nothing to do with each other, completely different. Completely different. The proofs that all these are Q-ish are also very different. So it seems that we have three very, very different reasons why a monad might be Q-ish. In fact, it is not very difficult to show that here nothing lives. So these conditions are not only incomparable, they're actually, these two are actually disjoint, but they are still sufficient for the property that we're interested in. There are also some cases that do not satisfy any of these sufficient conditions, but are still Q-ish. We know 4 of them, actually exactly 4 of them. So the reader monad is one of those. And the proof is completely different from it relies on a compactness argument, on the fact that on a finite alphabet x to the omega is a compact topological space, and we use this compactness to sort of restrict the case of languages recognized by finite T algebras for this monad. The free lattice monad also doesn't satisfy any of the sufficient conditions, but it is Q-ish. And the proof relies on a convexity argument very specific to the theory of lattices. Okay. Another example is the single binary operation subject to this equation. And here, okay, power set this is not weakly Cartesian, and the power set construction does not work, but the power set squared construction works. Another trick works. And finally, we have a crazy example like this. So this is a monad. This is my favorite example here. So this is a monad we took from the literature. 2 Euler operations and 2 equations that look bonkers like this. So this monad is pathological in that it has no non-trivial finite algebras. It has lots of infinite algebras, but the only finite algebra has only 1 element, which means that no language is recognizable for this monad. Therefore, this class is very well behaved and so on. So this is crazy. So we have these four pathological examples here. We also have more counter examples than just the one. Counter examples, well, we also know 4, just to make it even with the sporadic examples. So first of all, monoids subject to this equation, they are wrong. They are not Q-ish. Then there is the marked words monad. Elements of Tx here are pairs, a word, just a standard finite word, and a multiset over the same alphabet, which is sort of smaller than the word, meaning that at most, it contains at most as many letters of this kind as are present in the word. This can be seen, the elements of Tx can be seen as words where some letters are marked, but we don't know exactly which ones are marked. We only know how many letters of each kind are marked. This turns out to be a monad. It's not very easy to, it's not very difficult to show, and it is not Cudish. Another one, the balanced associativity monad. So single binary operation and an equation like this, another counterexample. And finally, the sort of half-hearted attempt at constructing a Maltsevian monad. So a monad presented by a single ternary operation and an equation like this, but without the equation that this is equal to y. Okay. So if I added this here, then it would be immediately a Maltsevian monad. It would be Cudish. But with this, it's not. And these are actually the only 4 examples that we know that do not satisfy. Again, all these counterexamples are very varied, and there is, at least it's not clear to me what is the pattern here. So this is the picture that we have. And I think this picture means that we actually have something that looks like a good notion. This. It is useful somewhat, because monads that satisfy this property, well, for those monads, a very reasonable abstract definition of monadic second order logic makes some sense. If this property doesn't hold, then this logic doesn't make sense. But when it does, the logic makes some sense. It satisfies certain, it passes certain sanity checks. It is implied by very varied conditions, and we don't have a very good characterization of this condition in terms of simpler notions. Now, if you ask me to simplify this property, then perhaps there are some ways. So, for example, if I drop the subjectivity here, and if I require that finitely recognizable languages are closed under direct images of all letter-to-letter homomorphisms, then some of these sporadic examples fall out. The free lattice monad is not the case. It is not QD anymore, and similarly for the reader monad. Now here, I will probably hope that this one example, which is not weakly Cartesian, can be put in the same basket with the weakly Cartesian ones, because okay, power set doesn't work for it, but something like a power set, or perhaps double power set or square power set, does. So perhaps there is some theory here. This thing here, this just stares us in the face laughing. There's no way out of this pathological example. But anyway, there are perhaps some way of simplifying this complicated picture, but this is future work. For now, the picture is very complicated, and that's all I want to say. Thank you very much for your attention.
Okay, thank you very much, Bartek, for a fantastic talk. So as is traditional, I'm now going to unmute everybody so that we can applaud Bartek and thank him for a fantastic presentation. That. So do we have any questions for Bartek? If you do have a question, please raise your hand. You can find that option under the participants menu. If you just raise your hand in your video, I might not spot that. So I mean, for now, Bartek, I have a question. Why do you, what gives you confidence, or maybe you don't have confidence, that there will be some clean algebraic properties that you can use to characterize these monads? Sorry, Bartek, you're muted. I've unmuted you. Go ahead.
Yeah, so by now I have lost that confidence, which yeah, I would be a bit surprised if there was a clean algebraic characterization of exactly this property. But to me, I just begin to think that this just means that this is an interesting notion.
What would the significance be of a clean algebraic property, or the lack of a clean algebraic property? I mean, in terms of the applications of these ideas.
Well, no, if there was a clean algebraic property, then it would make for a nicer theorem about when monadic second order logic makes sense for which monads. So it would be a shorter and nicer theorem. But then this notion would disappear. I would be glad to get rid of it, but I don't know how.
Mm-hmm. And I mean, do you have any application, these sort of exotic, wild examples? Do you have some idea of applications or something exciting that could be done with them?
Right. So, okay. So the idea of doing monadic second order logic on various kinds of structures has been around for a while. But of course, people who study that are interested in a lot more than just the correspondence between MSO definability and recognizability by finite structures. So this is just a very initial step, which is interesting because we are already a bit stumped by simple obstacles. But once this is understood, then the next step would be to understand the second implication. So for example, if you remember, can I go back here? If you remember my slide about my abstract definition of MSO here. Mm-hmm. This is the definition of, this is an abstract definition of monadic MSO. Okay, but it is still not fully monadic because there is this language. There is this language here which is very word specific. So these properties of what it means to be the class of MSO definable languages, these are generic, as we've shown. This is the very word specific. So we know now that if we take a family of recognizable languages and we close it under these operations, for Q-dish monads, we are recognized by finite algebras. Mm-hmm. So this is the left to right implication here. But of course, for the other implication, the question would be, can we choose, for which monads can we choose a finite number of specific languages so that this left to right implication becomes an equivalence? Mm-hmm. That's a much harder question. And actually, hopefully, perhaps, when we study it in detail, several examples of Q-dish monads that are problematic to us will just drop out of the picture. And then actually, for the more complicated case, the characterization might potentially become simpler. There is some hope to that. Okay. Then, of course, once we have this, there's definition of how can we prove that the monadic second order logic is decidable, for example. Mm-hmm. And ultimately, decidability of this logic is what people are after. But this is very far ahead. We're having problems with very basic structural properties. Mm-hmm.
Okay, and we have a question now from Pavel Sobocinski. Please go ahead, Pavel.
Hi, Bartek. Thanks for the great talk. So actually, my question is related to the last thing you said. So you started off by restricting your focus to the logic and the monoids, right? So to get to the monadic logic and the monadic monoids, i.e. algebras. But what about notions of automata and notions of cleaning algebra for these things? So how does that generalize to these more wild T's?
I have no idea. This we do not touch.
Because I guess that would be related to decidability. Once you have sort of models of state machines for these various examples.
It could be, yeah. Mm. So this we consciously do not touch, focusing on just the bit of MSO versus algebraic recognizability. The whole story of what it means to be an automaton, which by the way is probably a co-algebraic side of the world, or a regular expression, that's not part of this story of this picture at all so far.
And I have a quick follow-up question. So you didn't say the word nominal for your whole talk. So is that because the nominal just doesn't fit into this picture, or?
No, it does. You just need to move from the category of sets to another category, which I
Okay.
in this presentation.
Okay, nice. Thank you.
Thanks very much, Pavel, for your question, and let's all thank Bartek again, if I unmute everybody.